Okay, good afternoon, Professor. My name is Ming, and this is my explanation for the fifth project of this course. The fifth project is the man-wolf-goat-cabbage traveling problem. So let me just explain what it is first from the book. A man is traveling with a wolf, a goat, and a cabbage. He comes to the west bank of a river and wants to cross. A tiny rowboat is available, but it is so small that the man can take at most one of his possessions with him in the boat. If he leaves the goat and the cabbage alone together, the goat will eat the cabbage. If he leaves the wolf and the goat alone together, the wolf will eat the goat. How can the man get to the east bank without losing any of his possession? So this problem is solved using the Prolog language. And here is my code. Before I go in depth into what the code does, let me explain a bunch of stuff. So we have the atoms, west, east, the compound term, which is an array or a list of 4 elements. For the problem, we have to convert this list into this list without having any of the possession eating each other. The first element of the list represents the man, the second represents the wolf, the third represents the goat, and the fourth represents the cabbage. To start, first I define two predicates which change the direction of each of the atoms from east to west if the pattern matches this, or west to east if the pattern matches this. It's used in my move predicate, which takes in a config, what to move, and also the new config. It returns the new config. So there are 4 cases for this move predicate. We have the case where we're moving wolf with man. As you can see, the first and second element, the wolf and the man, are moved together. And we use the change predicate to change their direction from west to east or east to west. The second move moves man and goat instead of man and wolf. The third one moves man and cabbage, and the fourth one moves only man. Okay, let's move on to the third predicate. So the third predicate is 1 equal. It checks to see whether this first variable is equal to this second variable, or if it's equal to this third variable. It's a very simple equal function or predicate. In Prolog, call it predicate. But despite its simplicity, I would like to explain how it works. So given this compound term here, if we call 1 equal on man, let's say the first element represent man, goat, and wolf. So that is man, goat, and wolf. The first pattern of 1 equal checks whether man is equal to goat. What do I mean by the first pattern? The first pattern is this. The second pattern is this. Going back to the example. So it first checks to see if man is equal to goat. Is man equal to goat? Yes, this one returns true. And then it checks to see if man is equal to wolf. Man is not equal to wolf, and it will return false. But here's the thing. 1 equal have 2 patterns, right? It puts them in a logical OR. So look something like this. 1 equal x underscore, or 1 equal x underscore x. So despite the case that man is not equal to wolf, this whole 1 equal expression is still true because man is equal to goat. Now that I got 1 equal out of the way, let's explain the safe predicate. The safe predicate takes the compound term, the list, man, wolf, goat, and cabbage. These are variables. Their values are atoms, either E or W. So this safe predicate calls 1 equal twice. First, it checks to see if man is with goat or with wolf. Second, it checks to see whether man is with goat or with cabbage. If I were to write this in a functional programming language or a declarative programming language, it would look something like this. Let's say I have a constant is safe, and I initialize it to this value. I call the 1. I call man is man equal to goat, or man equal to wolf. Well, that's the first 1 equal line here. And then I logical AND this expression with man equal to goat or man equal to cabbage. And as you can see, it does a pretty good job. If man is not with goat and he's on the other side of the river, then the state is not safe anymore and this entire expression is false. If man is with goat, then the entire expression is true. Because as you can see, we check man is with goat twice. One on the left side of the AND operator, the other one is on the right side of the AND operator. If man is with wolf, then it's not safe because, well, the goat will eat the cabbage. Oh, one more thing before I move on to my solution. This compound term here represents the next config. So as you know, when you call move, it creates next config. Next config will be passed to safe, not previous config. Okay, that's it for the two very important checks of this code. Now let's move on to the solution. The solution has two patterns. The first pattern is the base pattern, where the next config is all is. When the next config is all is, the solution has been found. The second pattern takes in the config and then it destructure a list into move and into the tail of the list. This is similar to ML's list destructuring, where you have something like this. X is the head, XS is the tail. This is Prolog's list destructuring. So in the second pattern, move predicate is called on move, which is the head of the list. So this move here can either be a goat, can either be a wolf, can either be a cabbage or nothing. Just know that it will move. It will take the original config and produce the next config based on one of these four predicates. Then it checks whether the next config is safe, and then it recursively calls solution on the rest of the list. Now I've run this program already, and as you can see, it produces around 32 solutions before finding no more. But the problem is we can see that the solutions are duplicates. 16 for this solution here and 16 for these solutions here. The way to fix that is to change the one equal predicate. One equal checks when the program backtracks to find another path to the solution. One equal triggers twice, which duplicates the solution. The one way to stop one equal from triggering twice is to define it as one predicate. This is my solution. So it checks whether x is equal to y and x is not equal to z. All right, this semicolon here is like an or. So or it checks whether x is equal to z and not equal to y, or x is equal to y and equal to z. So this predicate here can only produce one true or false. No matter how many times the program backtracks, it can only call this once. It can only be matched with this one time. So it creates a unique solution. Let me show you. We see that there are two unique solutions and the program ends right there. So this is it for my project. Hopefully it makes sense, and I hope to see you in the next project. Goodbye.